Welcome to the TVE Happy Math Hour, our weekly interactive and reviews for Math 1314 and Math 1324, presented by Yvette Chuca, Ruben Carrizales, and Albert Isasi. The session will be recorded so that you may come back to it later if you need to, and so others that have missed out on today's events will be able to watch it. Um, this event will provide Tejano Passport points. This code will be posted on the chat at the end of the session for the Tejano Passports. Shortly, you will see the link to the Math 1324 for those that are interested in participating in that session. So now at this time, please mute your mics for the best sound experience. Otherwise, the feedback could interfere with information that we will be sharing today. Without further ado, here is Ms. Chuka.
Hello, everyone. Welcome to Friday Happy Math Hour. So today we're going to go ahead and we're going to look at linear systems of inequalities. And then if we have time, we'll jump into the matrices. And so we'll just get started here. The last time that we met for Friday Happy Math Hour, we talked about systems of equations. And so we learned that in order to be a system, you have to have two or more equations. And then the only difference today is that instead of equations, we're going to have inequalities. So remember that an inequality has a less than or equal, a less than or greater than sign, or a less than or equal to sign, or a greater than or equal to sign. And so these are two examples of inequalities. An ordered pair is going to be a solution to an inequality if it's true once we substitute those values. And then we're going to go ahead and collect all the solutions for those inequalities by shading the graphs, and you'll see that in a second. So whenever we graph lines, if I go back to the previous slide, if you have a less than sign or a greater than sign, when you graph the line, it's going to be a dotted line. As you can see here on this graph, for this equation, it's going to be a dotted line. If you have a less than or equal to or a greater than or equal to sign, then when you graph the line, it's going to be a solid line. Okay, so those are some decisions that you will have to make once you're ready to graph. The next thing that we're going to do is once you graph both equations, wherever they intersect, so in this darker shaded area, this is part of the blue graph here, but it's also part of the pink graph here, or the dotted line or the solid line. So this area that is in a darker shade where my mouse is, that's going to be the solution to the entire system. Okay. So to graph these, again, the first thing is decide if you're going to do a dotted line or solid line. And then we're going to select the test point so that we can test if where the solutions are. So let's try an example. So we have sketch the graph of x plus y is greater than 5. What we can do is replace the inequality with an equal sign. And then this should be a review from chapter 1, right? In chapter 1, you learn how to graph lines either by using a plotting method or the intercepts, or even the slope and the y-intercept. So for this example, I'm going to go ahead and use the x-intercept and y-intercept. So for the x-intercept, this is when we let y equal 0. So if y is replaced with 0, we get x plus 0 equals 5. And so x is going to be 5. So our ordered pair here would be 5 and 0. And then the y-intercept, we're going to let x equal 0. And so we end up with y is equal to 5. So if I plot those 2 points, then we're going to also need to decide if it's dotted or solid. Since the inequality is greater than, then we're going to use a dotted line. And so here's a picture of my graph. So here we have our x-intercept, our y-intercept, and then we have our dotted line. The step number 2 is going to be to pick a test point. Now you can pick any test point that you want as long as it's not on the actual line. The easiest test point to pick, if it's available, is 0, 0. And you'll see why here in a second. So again, as long as your point is not on the actual line, then you can pick it as a test point. So let's select 0, 0 as our test point. I'm going to put a dot here just so that we can see where it is. Whenever you're graphing on your computers, you don't want to put the dot there because it's not really part of the graph. It's just for us to reference. Okay. So what you do with your test point is we take our inequality, and x is 0 and y is 0. So 0 plus 0 is greater than 5. And this is a false statement. 0 is not greater than 5. If you get a false statement, then we're going to shade the opposite side of where the test point is. So if my test point is here, the opposite side of that is going to be on top of the line here. So your solution would be all this area where my mouse is. What exactly does that mean? What this means is you can pick any point in this shaded area, and if you plug it in for x and y, it's going to give you a true statement. Okay, so any of these points here is going to be a solution. And the points on the actual line are not solutions because it will make the inequality false since it's a dotted line. So let's look at this one. What I like about this section, it kind of helps us to review topics from previous sections, right? So if you look at this equation, we're not working with the line. Instead of the x squared and the y squared, we're working with the circle. And so what we want to do is first we're going to replace the sign with an equal sign. And then our goal is to graph it. Okay, so in order to graph this, we need to know what the center is and what the radius is. So here we have our standard form. And so from this standard form, we can get our center. So h is 2. And then for k, we're going to get -1. Okay, so it's the opposite of what you see in the equation. So we're going to end up with a +2 and a -1 for our center. Now the radius, we're going to have r squared is equal to 9. And so if we have, let me just write that out here. If we have r squared is equal to 9. And if we solve for r, excuse me, then we get that r is equal to 3. Since we're looking at the distance there, we take the +1, r equals 3. And so now we know our center and we know our radius. So to graph this line, we would go to the center, which is 2 and -1, which is right here where my mouse is. And then from that point, we're going to go up 3 units, and then we're going to go down 3 units, and to the left 3 units, and then to the right 3 units. Our inequality is less than or equal to, so we need to decide if it's going to be solid or dotted, and in this case would be solid. Okay, let me go back here. All right, so if we want a test point, again, 0, 0 is available. So if it is available, then we can use it. And if we plug it in for our x and y, then we get 0 minus 2 plus 0 plus 1 squared is less than or equal to 9. That gives me a -2 squared plus a 1 squared is less than or equal to 9. -2 squared is 4. 1 squared is 1. So 4 plus 1 is 5. 5 is less than or equal to 9. That's a true statement. So we're going to shade where the test point is located. So my test point is right here. So that means that I'm going to shade all of this area here. Okay, so that would be our solution, the shaded part. Now in this example, any point on the line would also be true. So those are also solutions. But what if we have a system? So those previous examples were only by themselves. So now a system, we have 2 equations here. We have a line and a parabola. So we just graph them one at a time. So we'll start with the first one. I'm going to change my inequality to an equal sign. And I'm going to graph using the x-intercept, y-intercept. So if y is 0, then we get -x equals 1, divide by -1. So x is equal to -1. So my x-intercept is -1, 0. And for the y-intercept, we let x equal 0, so we end up with y is equal to 1. If we graph the line, we're going to use a solid line because of the inequality sign. And so this is my line here, 0, 1, and negative 1, 0 are my intercepts. And if you're doing this on paper, I do encourage you to have two different types of a pencil and maybe like a different pen, or if you have two pens, make one a different color. Okay. And so once you do this, go ahead and find the test point for that line. So my test point, I can use 0, 0. And I'm going to decide what part I need to shade. So if x is 0, y is 0, we get 0 is less than or equal to 1, which is a true statement. So I'm going to shade the side where the test point is located. So all this area would be shaded. And so this is what it would look like. And so that's only for the first equation. So now we need to graph the second equation. So the second equation is a parabola. And so we have here, replace the inequality, and you can find the x-intercept and the y-intercept. So here we have, or you can use transformations to graph it. It's up to you. So I have my two x-intercepts, and if x is 0, then y is going to be, let me see here. So if we have negative 1, it's less than or equal to 1. And then if we divide by negative 1, our inequality should switch. That should be greater than or equal to negative 1. Well, since we're looking for the intercepts, we shouldn't even have our inequality in here, right? It should just be an equal sign. So let me scratch that out really quick so we don't get confused. So this right here, you want to replace it with an equal sign. Okay, so all of these we're going to replace with an equal sign. And so our y-intercept will still be a 0, negative 1. Our line should be solid. And so I plot my x-intercept, my y-intercept, and my y-intercept and my x-intercepts. And now we're going to pick a test point. Okay, so test point, the question, can I use 0, 0? Yes, because it's not part of the graph. So if we replace 0 with x, or x with 0 and y with 0, we get 0 is less than or equal to 1, which is a true statement. So that means that I'm going to shade everything inside of this parabola. And so now that we have both graphs, we can come back and look at both of them. Okay, so what I like doing is I like to graph these on the same plane. And the reason for that is so that I can see where they intersect. Since I was using the computer, this is why I have them, I did them on a separate one. But if you do them together, then your graph is going to look like this. And notice that when we put the graphs together, this area that I have where it says solution, that's the only solution for the system. So any points that are in here would be your solution. So anything in the blue area, that's the solution for the parabola. And anything in the pink area is the solution for the line. And the solution for the whole system is this darker area. Okay. And so like what I tell my students is, if you're taking a test, just make sure you really identify what the solution is, either by highlighting it or writing the word solution. Let's try another one here. So I have x plus y is greater than 3. I'm going to change it to an equal sign. I'm going to use the intercept. So when y is 0, x is 3. And when x is 0, y is 3. I'm going to be using a dotted line since my inequality is a greater than symbol. And so I plot my line. Here are my 2 points. And then I'm going to go ahead and graph the second equation, or use the test point, right? So 0, 0 is my test point. If I plug it in for x and y, I get 0 is greater than 3. And that is a false statement. So here's your test point, but we got a false statement. That means we shade on the opposite side, which is going to be all of this area here. The second equation, x plus y is less than negative 1. Change it to an equal sign. If y is 0, then x is negative 1. If x is 0, then y is negative 1. So if we graph our 2 points, I'm going to use a dotted line since the inequality is still less than, and then we're going to pick a test point. So my test point, I have 0, 0, so 0 is less than -1. That's a false statement as well. And so I'm going to, if my test point is here, I'm going to shade on the opposite side, which is all this pink area. If I see the graphs together, if I put them on the same plane, then this is what we have, right? So the question is, where do they have the same shading, or where do they intersect? And they don't, right? So the shading here for the pink line does not intersect with the shading in the blue area. And so what we say is that there's no solution. So there's never going to be a point that is going to work for both inequalities. Okay? And so those were just some quick examples that we wanted to share with you. Let me go ahead and upload the matrices stuff. That way we can start with that. In the meantime, while I pull it up, if you have any questions, feel free to ask us. Let me just get the file really quick. And here it is. Let me just download it really quick into the computer. Okay, so now I'm going to upload it. Share files. Is there any questions? And it's loading right now, so. Okay.
Excellent, Ms. Chuka. So I can take over if you want.
Okay. Thank you, Ruben.
All right. All right. So so let's continue again for our classes. We have also starting chapter 8, 8.1. So let's go ahead and review what 8.1 is all about. So 8.1 is introduction to matrices. So my question to you all is, what is a matrix? Okay, so again, a matrix is a rectangular array. Now, what I like to always tell my students is a matrix is kind of like a good way to hold information and keep it in order. Okay, so I used to say it was like an address book, but nobody uses address books anymore. Our phone is our address book now that has all the information about our contacts and our numbers and friends, right? But this is what a matrix is something to hold information, and it keeps the information in an order. Now, an example of this rectangular array, first, to help you is when we're introducing matrices, we're going to put now a bracket. So when you see these square brackets, you know that we are dealing now with a matrix, okay? And then the numbers in here, we call these elements that are inside the matrix. So again, this matrix has these elements 4, 5, -1, 0, okay? Now, a little bit more detailed or a little bit more official definition of a matrix is, again, you have a rectangular array, and the reason why this holds information in order is because the matrices are arranged in this format. We have rows and columns, okay? So the number of rows and columns tells us the type of matrix we have, and this is considered the size of the matrix or the dimensions of the matrix, which I will go into a little bit more detailed, okay? But again, when dealing with a matrix, okay, the elements in here will go in each specific field or address. Okay, now we say it's A11, and what they're skipping here is we like to give names to matrices. Okay, so just like your name, we capitalize the names. So the common names that you're going to be seeing when dealing with your homework is capital letter A, capital letter B, and capital letter C. Those are the most common names that we give the matrices, and just the uppercases A, B, and C. So for instance, in this particular matrix that they're just throwing in from our book, this we would consider the matrix A. We use capital letter A. So all of the elements inside, we use lowercase little a. Okay, so what these numbers here in the bottom mean, it doesn't mean 11. Okay, so this underscript means that this element here that has a 1 1, that means that it's in row 1, column 1. Okay, so for instance, this next one, this element A is in row 1, column 2. And again, this is how you're going to list the elements inside the matrix. Okay, they have a particular address. Okay, all right. So as I was saying to you, the way we're going to distinguish one matrix from another is from its size, or the true definition of the book, it says the dimensions of the matrix. And again, the dimensions of the matrix, or the size of the matrix, is given by the number of rows by columns. Okay, so for instance, in my first example here, I have 2 rows and I have 2 columns. Now, whenever you have, the same number of rows with the same number of columns, we call this a square matrix. Okay, so let's look at this next example. This next example, if you see, we have only 1 row and 2 columns. So whenever we just have 1 row, we call this a row matrix, and the size of this matrix would be a 1 by 2. Okay, now this third example here, you see we have 2 rows and only 1 column. So since we only have 1 column, we consider this matrix a column matrix. And again, the dimensions of the matrix is a 2 by 1. It's always the rows by the columns. Okay, you have to follow this order. The size or dimensions of a matrix is always rows times columns. Okay, now this last example you see here, we have a 2 by 2 matrix, which is a square matrix. But whenever we have these values, 1 0 0 1, this is what's called the identity matrix for a 2 by 2 matrix. Now, the best way to think of the identity matrix is this matrix is value of 1. You can think of it like this. You know, if I have only ones in the positions here, this is called my identity matrix. Okay, and I'll show you how we use this and more details on this. Okay. All right, so let's practice to find out if we have this down packed, determining the dimensions of each of this matrix. Okay, so let's look at A. A, if you see, we are dealing with a matrix. We have the square brackets, but we only have 1 row and 1 column. Okay, so which one would this be? The 1 row and 1 column refers to G, right? So I have G is 1 row, 1 column. B, I have 1 row and I have 1, 2, 3, 4. So I have 1 row, 4 columns. So the dimensions of B is a 1 by 4. That would be C here in purple. Okay. Then I have C. I have 2 rows and 2 columns, a square matrix. Okay, so 2 by 2. So the C would be B. This is a 2 by 2. And then I have D. D, I have 1, 2, 3 rows, and I have 1, 2 columns. So the dimensions of D is a 3 by 2. So the answer to that would be D. Yes? So this is how we find the dimensions of the matrix, or the size. This is how we know the difference between matrices. Okay? And it's crucial for us to do the dimensions, to do a lot of algebraic stuff with them. Okay? So first, since we have been covering linear systems, okay, and you've been solving linear systems, again, just to do a recap on that, there were several ways to solving linear systems. We have the graphing method, the substitution method, and we had also the elimination method. Now I'm going to introduce a fourth method on how to solve linear systems. And the first thing that we can do in order to solve linear systems in a different way is to convert the linear system into a matrix form. Okay, now because we are dealing with a linear system and we're going to do it algebraically, it has a specific name, and the specific name for solving linear systems using matrices is called an augmented matrix. We're going to convert our linear system into an augmented matrix form. Okay, and if you see here, the way we do it is like this. Okay, again, we are going to do brackets. This is going to indicate that we are using matrices. Okay, and then you see here the values of that have the x and y to the left of the equal sign. Okay, since our matrix has specific values, it has addresses that it keeps for us, and we don't have to tell it what these numbers represent. We don't have to say the x and y, so we're just putting in the coefficients into my augmented matrix. So for instance, if I look at equation 1, the first value here that would be in my position 1 1, again row 1 column 1, would be the coefficient 3, and then the next value would be 5, that is in the position 1 2. Okay, in augmented matrix, in matrices, the equal sign is represented by this line. This means equal, okay, or it's called a pipe. Okay, so but this line here is the representation of the equal, so that equal, and then I just put the value here to the right of the equal sign, which is a -9. Then let me go to row 2. The coefficient for this row 2 column 1 would be 1, and then the coefficient for the row 2 column 2 would be 4, and then I have my equal sign, and then to the right of the equal is a -10. So what I just did was converted my linear system into a matrix form, which is called an augmented matrix form. Okay, very, very easy. You may have a test question just to do this simple thing. Convert a linear system into its equivalent augmented matrix. Okay. All right, so let's practice some more. The question is telling us, write the augmented matrix for the system of linear equations given here on the right? So let's go ahead and do it. So first, and then it asks us to find the dimensions of the matrix, and we'll do that at the end, okay? So let's go ahead and convert this linear system into its augmented matrix form. All right, so the first thing that I need to do is do brackets, okay? The brackets indicate that I'm dealing with a matrix. Again, my equal sign is represented by this line right here, okay? So here, if you see here, I am dealing with x, y, w, and z values. I'm dealing with four variables, so I'm gonna put them here. This is the order where we have x, y, z, and w. And then my constant with a solution are going to be to the right of the equal sign. So these are these values, 9, -2, 0, and 4. So let's go ahead and do them, okay? So I'm going to do them one by one, okay, just so you can see what I'm doing. So here, this is line 1. So line 1, I have 1 for the x. I have a coefficient of 3 for the y, but I don't have a z term. So since I don't have a z term, I'm going to put 0 here. I need to keep a placement value. So that's 0. I don't have any z for that first row. But then the coefficient for the w is a -1. Again, the equal sign to my constant, 9. Okay, that was row 1. Let's look at row 2 on my matrix now. I don't have an x term, so I'm going to represent that as a 0. And then I have a -1 for the coefficient for the y, a 4 for the z, a 2 for the w, equals the constant, -2. Okay, now line 3. Again, I have a 1 for the coefficient for the x. I don't have a y, so I have to represent that as a 0. Coefficient of -5 for the z, a -6 for the w, equals 0. Yes? Now, don't forget the zeros. If you forget the zeros, they're going to count the whole thing wrong, okay? So do not forget these placement values for zeros. All right, let's do our last line, line 4, okay? So for the coefficient for the x is a 2, the coefficient for the y is a 4, the coefficient for the z is a -3, and I don't have a w, so my w would be 0 here, equals 4. Voila. I converted a linear system into its augmented matrix form. So now it's asking us, what are the dimensions of this matrix? So it's the dimensions is the number of rows with the number of columns times the number of columns. So let's see, we have 1, 2, 3, 4 rows, and then we have 1, 2, 3, 4, 5 columns. So the dimensions of this matrix, or its size, is a 4 by 5 matrix. Okay. All right. So let's go ahead and solve. Now that I introduced how we can convert a linear system into its augmented matrix form, let's use this form in order for us to solve the matrix. Okay. Now, to solve this matrix, what I want to do is, again, just to see that this came from a linear system. Okay. So just to clear up the reason why I like to put this one on here too is most of us are doing the homework on the computer, and the computer doesn't have a way to put a line throughout the matrix. So what the computer does gives you the 3 dots. Okay, the 3 dots on the computer, it's the equal sign for us. Okay, so just to see here on this problem, it says write the system of linear equations represented by its matrix. So now let's go backwards. So again, here since I have 2 columns, that means that I have 2 variables, and the variables are going to be x and y. So again, let's go down to the first row. The first row is x is 6, y is a positive 5. Again, these dots is the equal sign in the computer, and it's to my constant 2. Let's look at my line 2. My line 2 is x is 3, so I have a 3x. I have a y for the negative 9, so it's a negative 9y equals 0. Okay, so this is a way to go from a augmented matrix to a linear system. Okay. All right. So let's practice again. Write the system of linear equations represented by the augmented matrix. Okay. So let's go ahead and do it. I think I'm missing something here. All right. So here I am missing the line here. Okay. So we have 2 columns here, the x and y. And I am missing, let me go ahead and let me see if I can add it myself. I am missing the equal sign here. Okay, so to convert this into its linear representation, again, when we're dealing with linear systems, we have a squiggly bracket. Okay, that's the difference between the two. A matrix has a square brackets, and the linear system has the squiggly bracket. Okay, so here for the first row, since I'm dealing with 2 columns, again, I'm dealing with 2 variables. The 2 variables are x and y. So I have 1 for x, but I have 0 for y. 0 times y is just 0, so that's why I don't write it. Again, I was missing my equal sign, equals 4. Then the second row, 0x. So 0 times x is just 0, and 1 times y is just y. So y equals 3. So I converted this augmented matrix into its linear system. Yes, into a system of linear equations format. All right. So now let's get into solving matrices using linear systems. Okay. So these are some of the syntax that we will use in order to solve. Okay. So one of the things that you can do is you can interchange rows, okay? And the syntax for that is, for instance, let's say I want to switch one row with another. The operation that we do is this double arrow sign. This double arrow sign means that I'm going to swap row A, whatever that is, whether it's row 1 or row 2, with this other row, which whatever number row that is, okay? That's one of the operations that we can do, and this is called elementary row operations with matrices, okay? The second one is we can multiply a constant to one row, but if we do this, again, make sure that we do this to the whole row, okay? So that means to both sides of the equal sign. Don't just multiply a constant to one side or the other, okay? So here it says that C cannot equal 0. We never want to multiply by 0 to something because then we cancel out the row, and that's not what we want to do. Okay, that's what this means right here. Okay, then now number 3. Number 3 says add a multiple of rows to another row. So we can add something that we multiplied a number to and add it to another row to make it into another row, or to make it into a different value row. Okay, and again, the best way to see this elementary row operations is with an examples to solve. Okay, so let me show you some of these concepts. Okay, so let's say that I have this original matrix here. Again, this matrix is 3 rows and I have 4 columns. This is a 3 by 4 matrix. Okay, so again, if I was looking at these 3 rows, this is row 1, row 2, and row 3. And what I can do is, one of the things I can do is I can interchange rows. Okay, I can make row 2 become row 1, and row 1 will become row 2. Again, the syntax would be the double arrow. So if I want to interchange them, the row 2 becomes row 2 is now row 1, which is -1, 2, 0, and 3. And what was once rows 1 is now row 2. Now it's 0, 1, 3, and 4. Okay, this is an example on how we can interchange rows. And again, these are equivalent matrices. I haven't done anything to it, but just swapped the rows. Okay, now this is an example of multiplying a constant to a row. Okay, so here, for instance, my original matrix row 1 is 2, -4, 6, -2. I can multiply this row by a 1/2. Okay, and the reason why I want to do this is because I want to simplify the numbers, right? So if I multiply this 1/2 to this row, again, I have to multiply this value 1/2 to all of the elements in the matrix. Okay, so 1/2 times 2 is 1. 1/2 times a -4 is a -2. 1/2 times 6 is a 3. And a 1/2 times a -2 is a -1. Okay, this is an example of multiplying a constant term to a row. Okay, and then the last example on how to add 2 rows together after I modified a row. For instance, here, this is the syntax. I'm going to multiply a -2 to row 1, add it to row 3 to get a new row 3. So again, the row 1, whenever I'm multiplying something to get a new row, that doesn't get altered. Okay, so just give you an example. My row 1 is 1, 2, -4, 3, but I'm doing something to it to modify row 3. So when I write row 1, again, that still stays 1, 2, -4, 3. That doesn't change. What's going to be changing is to the addition of the row 3. Do you see here? My row 3 was 2, 1, 5, -2, but I'm doing an alteration. I'm adding it to the multiplication of -2 row 1. So for instance, -2 times 1 is a -2. -2 plus 2 is 0. -2 times 2 is a -4. -4 plus 1 is a -3. -2 times a -4 is a +8. 8 plus 5 is 13. -2 times 3 is a -6. -6 times plus a -2 is a -8. And there it is. This is my new row 3 after this alteration. Again, this is an example of adding 2 rows together with an alteration. Okay, so to solve a linear, an augmented matrix form, what we want to have on this left side of the matrix is the identity matrix. And the best way that I like to tell students is the reason why we want to get this left side as the identity matrix. Think of what Ms. Chuka was doing to graph. If I wanted to graph a line, I start with the intercepts, right? I can find the x and y intercepts. So that's kind of what we're doing with matrices. Here, what I want to do is I want to find the single instant value for the x, and I don't want to get the y value. I want to be 0, and that's going to give me the x value that corresponds to this line, right? Similarly, for the second row, since the first one is going to give me the x, what I want to solve for is the y-intercept. I want this value to be 0, this be 1. This is going to give me the instance where y is equal to this intercept. So again, to solve augmented matrix, we want to have the left side be its identity matrix. Now, since this matrix is a 2 by 2 matrix, the identity is a 1 0 0 1. It's a 2 by 2 matrix. Okay, so the process of doing this, the process of converting this left side into a 1 0 0 1, this is called a reduced echelon form. Okay, and we're going to do row operations in order for us to get the solutions. So again, the solutions for x and y for this matrix using my row operations is x is 6/23 and y is 2/23. Okay, now the process, again, we are going to do this algebraically. It's called row operations. Okay, some calculators or some books also call this the Gauss-Jordan elimination. And what we do is we're going to do row operations in order to get our desired outcome. Okay, again, the solutions for this, as before, as Ms. Chuka mentioned, we have an ordered pair. Okay, and it's a point where these two lines intersect. We're still solving linear systems. Linear systems is all about where two lines intersect. And what does that mean? Is where these two lines share the same x value and y value. At this point, this is where these two lines intersect. So these two lines share these two values, which would give me a true statement. All right, so let's look and see. Let's practice. Let's go ahead and solve this system of equations, but let's use it using matrices. Okay, so my first step is to convert this linear system into its augmented matrix form. Okay, again, I need to have brackets. Okay, the left side is just the coefficients of the x and y. Since I only have two variables, I should only have two columns. So we have 2, 4 equals 8. Second row, 1, -1 equals 5. Okay, we're going to do row operations to get our goal to the left side, be the identity matrix, 1 0 0 1. When I do this, I'm going to get the solution of A and I'm going to get the solution of B. Again, this is my X and Y answers. All right, so let's go ahead and do it. The first thing that I want to do is, since the goal is to have a 1 here, let me use one of my basic fundamental row operations. I'm going to make row 2 become my row 1. So this is the syntax. Row 1 is interchanging with row 2. And I did it here. My new row 1 is 1 -1 equals 5. I'm missing the pipe again. And the row 2 is 2 4 equals 8. Okay? All right. Now the next step is I want a 0 here. Now, let me give you a piece of warning. When we're solving for the systems using matrices, you have to follow this order. We have to go column by column, just like the way you read a book. We go from left to right. That's how you have to solve these. We have to go from left to right. So that means we have to go the column first, the 1 and then the 0. Then I have the 0, then the 1. If you break this order, you'll go in circles and you'll never solve it. Always have to go in this order from left to right. Okay. All right. So my next order of business is this 2 needs to become a 0. So again, I'm going to use my fundamental row operations. What I'm going to do is I'm going to multiply a -2 to row 1. And you see here, if 1 was a -2, opposite of 2, and when I add these two together, I am going to get 0, and it's going to give me my new row. So again, it's a -2 to row 1. I'm going to add it to row 2. And this arrow means that I'm getting the new row 2. So what I tell my students, I am getting a new row 2. Row 1 is not getting altered. Nothing's happening to it. So the first thing that I do to solve these is I write row 1 first. I write it down since nothing's happening to it. It's 1 -1 5. But let's go ahead and do this process. I'm multiplying a -2 to row 1. So again, I'm multiplying this -2 to all of the elements inside my matrix. So a -2 times 1, a -2 times a -1, and the -2 times 5. Yes? So when I do that, again, I get a -2. A -2 plus 2 is 0. There it is. Okay? Then a -2 times a -1 is a +2. 2 plus 4 is 6. Goes right there. And then a -2 times 5 is a -10. -10 plus 8 is a -2. That goes right there. Oh, see, my pipes come on. So they were a little late in the animation, right? So here, I have this first column, what I want. I wanted a 1 0. Now I want a 0 1 here on this column. Okay, so what I'm going to do first is go ahead and simplify my row 2, okay? So I want a 1 there. So what I'm going to do is I'm going to multiply a 1 over 6 to row 2, and that's going to give me my new row 2, okay? So again, nothing's happening to row 1. So the first thing I do is I like to write my row 1 first, okay? But that's 1 negative 1 equals 5. But then I'm going to do this process. I'm going to multiply a 1, 6 to row 2, and that's going to give me my new row 2. So let's do this. 1, 6 times 0, that's 0. 1, 6 times 6, 6 divided by 6 is 1. Then 1, 6 times a negative 2, a positive times a negative is a negative, and that gives me 2 over 6, but I want to always simplify. 2 will go into 2 one time, 2 will go into 6 three times. So I have negative 1/3, and I already have one solution, y equals negative 1/3. But again, let's get the next one. I want to make this equal to 0. To make this equal to 0, all I have to do is add these two rows together. I don't have to multiply anything. Hopefully you see that. So if I add row 2 with row 1, that will be my new row 1, and that's going to give me the desired outcome that I want. So let's go ahead and do it. Again, nothing is happening to row 2. I already have my solution for that, okay? So I always tell my students, write this one first. Write 0, 1, negative 1/3, and then do this operation. Let's go ahead and do this addition. 0 plus 1 is 1. 1 minus 1 is 0. And negative 1/3 plus 5, again, we have to get a common denominator. I would convert the 5 into 15 over 3. So minus 1 plus 15 is a positive 14 over 3. So voila. I used matrices to solve my value for x and y. My value for x is 14 over 3. My value for y is a negative 1/3 again, but this should be an ordered pair, okay? So I would write it as an ordered pair. Okay, I think I have a time for one more example. Let's do one more, okay? So let's go ahead and use matrices to solve this one. Use matrices to solve negative 3, 4, 6, negative 4, and to equal to this 22 and negative 28. Again, our goal is here on the right hand side. I want to make the left side be my identity, 1, 0, 0, 1. And when I do that, I'm at my solution. All right. So the first order of business, I want this value here to be a 1. So I'm going to multiply row 1 by a negative 1/3, and that's going to give me my new row 1. Again, the first thing, I know it's not visible here, but again, what I tell my students, the first thing you need to do when you're writing the matrix is write the row 2. That one's not getting altered. I'm not doing anything to it. That way you don't get confused. So I write 6, negative 4, negative 28. But I am getting a new row 1. So let's do it. Negative times a negative is a positive. 3 divided by 3 is 1. There it is. Okay. A negative with a positive is a negative. And 1/3 times 4 is just negative 4/3. Okay, a negative with a positive is a negative. 1/3 times 22 is just 22/3. So it's a negative 22/3. All right. So I got this value down. Now what I want is, again, I'm going in order, the column by column. Now where the 6 is, I need this to be a 0. So what I'm going to do is I'm going to multiply a negative 6 to row 1, and I'm going to add it to row 2. That's going to give me my new row 2. Again, the first thing that I do is I write my row 1. That one's not getting altered. Nothing's happening to it. So just leave it alone. But let me do this new modification. The first thing I'll do is I'm going to multiply a negative 6 to row 1. So negative 6 times 1 is a negative 6. Negative 6 plus 6 is 0. Goes there. Multiply a negative 6 to the negative 4/3. A negative with a negative is a positive. 6 divided by 3 is 2. 2 times 4 is 8. 8 plus 6, and I'm writing it, but I'm not showing you. 8 minus 4 is 4. That goes right there. Yes. And then the last multiplication, the negative 1/3 times the negative 22 over 3. Okay. We can simplify. We get 44 minus 28 equals 16. That goes there. Okay. So I got my first column. Now I need to go my second column. Again, I want a 1 here and a 0 here. So let's get the 1 first. So what I'm going to do is I'm going to multiply a 1/4 to row 2, and that's going to be my new row 2. Again, row 1 is not getting altered. It's just 1 negative 4/3. So again, I'm missing the pipe again, equals negative 22 over 3. But let's get my new row 2. Multiply the 1/4 to all of row 2. 1/4 times 0, that's 0. 1/4 times 4, 4 divided by 4 is 1, and 16 divided by 4 is 4. There's my new row 2, and I have my solution, y equals 4. Again, just like before, and let's get the x. I want to make this value here a 0. So to do that, I am going to multiply row 2 by a positive 4/3 added to row 1. That's going to give me my new row 1. Again, I like to write row 2 first. That one's not getting altered. I already have a solution for it. So I'll put it there, 0, 1 equals 4. My pipes are back. Okay, let's do the math. 4/3 times row 2. So 4/3 times row 2 is 0. 0 plus 1 is 1. Okay, there it is. So let's do it again. 4/3 times 1 is 4/3. 4/3 minus 4/3 is 0. That goes there. Okay, and then the last multiplication, we're gonna end up with 16/3 minus 22/3. Again, I have the common denominator, so I get a negative 6 over 3, which equals to a negative 2. Goes there. So my solution for this, since I have my identity now on the left side, gives me the values for the x and y. So again, x equals negative 2, y equals 4, but again, never put them like this. This is an ordered pair. The solution should be negative 2, comma 4. Yes? Okay. Now I'm going kind of fast because I think this is straightforward. Again, for those of you who have joined us, again, you can have a copy of the download of the presentation. Just click on the little box with the arrow going down, and you'll have a copy of this. Okay, so I still have 8 more minutes, so let me keep on going. Okay, so I love to do math, as you can tell, right? So let me move into section 8.2 just to give you a brief introduction to get you started. Okay, so what we're going to do in this section is we're going to do matrix operations. Okay, so what are these matrix operations? So we're going to do fundamental math, which is I'm going to show you how to add, subtract, multiply matrices together. Okay, well, not the matrices yet. What I'm going to do is I'm going to do scalar multiplication. So these are fundamental things that we can do with matrices. Okay, but the first thing that I need to point out, in order for us to do any of these basic operations, is we need to be dealing with equal matrices. And what that means is the only way that we can do these basic math operations with these matrices if they have the same dimensions. It's like we're going to be adding and subtracting, and when we're adding and subtracting, we have to have like terms. The representation of like terms with matrices is that they have to be equal to each other, and equal to each other means that they have to have the same dimensions or the same size. The same number of rows and the same number of columns have to be given to when we're adding and subtracting matrices together. Okay, so that's the first thing that you need to do. So a quick representation, again, I may be able to do A, B, and C here. Okay, so here, if you see here, I have two matrices and I named them. I have matrix A, matrix B. So the first thing that I have to do is look at these matrices. What are the dimensions, or what are the size of these matrices? So matrix A is a 3 by 3 matrix. This is a square matrix. The same number of rows with the same number of columns is called a square matrix. Okay, so the size of matrix B, or the dimensions of matrix B, is a 3 by 3 matrix as well. 3 rows, 3 columns. So these are equal to each other. So hence, I can do some basic math operations with these because they're the same size. So let's do an example of what's called a scalar multiplication to a matrix. So I want to do A, 3A. So what this means, the 3A means that I'm going to multiply 3 to every element inside the matrix, or every address inside the matrix. Okay, so the way I do it is here listed. This 3 is going to be multiplied to all of the elements in here. 3 times 2, 3 times 2, 3 times 4. And when I do that, it's going to give me my answer. So again, 3 times 2 is 6, 3 times 2 is 6, 3 times 4 is 12, 3 times 3, and negative 3 is a negative 9, 3 times 0 is 0, 3 times a negative 1 is a negative 3, 3 times 2 is 6, 3 times 1 is 3, 3 times 2 is 6, okay? So this is an example of just a simple scalar multiplication that I can do to a matrix, okay? The second example is multiplying a negative 1 to the matrix. Again, this is still, this is called the negative matrix, okay? Sometimes on your homework, they're gonna ask you, what is the negative inverse of the matrix? All that is is you multiplied a -1 to the matrix. Okay, so here I multiplied a -1. So again, I'm gonna for every element, I'm just gonna multiply that -1. And again, so I just changed the sign of all my elements. Okay, but the most useful or probably possible test question is you're going to have to add two or subtract two matrices together. So on this particular one, I'm just using what I've done. Okay, I will add 3A, matrix 3A, subtracted with matrix B. Okay, so to do that, very, very easy. The way we're going to do this is I already have 3A, this is this matrix, and you can think of it as the addition of the negative B matrix, right? That's the other reason why I did the negative B, so I can do the C part, okay? So I could have left it as a subtraction with a regular B, but since I have a negative B already, I think it makes more easy for explanation purposes. But again, to do this operation, what you have to do is you have to add the same address with the same address of the other. What do I mean? So for instance, this value 6, this 6 is in the row 1, column 1. This 6 has to be added with the same address of the other matrix, which is the row 1, column 1 of the other. So to do this operation, again, I'm going to go through the process. 6 plus a -2 is a 4. 6 plus 0 is 6. 12 plus 0 is 12. Minus 9 plus a -1 is a -10. 0 plus 4 is 4. Minus 3 plus a -3 is a -6. I'm in the third row. 6 plus 1, 7. 3 plus -3, 0. 6 plus -2, 4. Okay? So the way you add two matrices together is first they have to be equal. What that means is they have to be the same dimensions or the same size. And then to do the addition or subtraction, whichever you're doing, you have to add the same element address with the same element address of the other. Okay, super straightforward stuff. Okay, again, this is all I have for you today. I want to thank you again for joining us for our Happy Math Hour. Guys, we're almost done. We have 2 more weeks till the semester is almost over, until we get to finals week. So hang in there. You all will do great. Again, I'll pass it back to our presenters. Thank you so much.
Okay, okay, thank you so much, Mr. Carrizales. That was a wonderful presentation on matrices. And if you have any questions, please raise your hand or type them in the chat. We have about 120 seconds to go. I would like to invite all of you to our next presentation at 1 o'clock today. Student Success will be presenting the EPCC honors programs at 1 p.m. And then next week, we are back with Happy Math Hour at 11. Math 1314 will cover inverses and determinants of matrices. And Math 1324 will cover basic concepts of probability, permutations, and combinations. Our student success topic for next week will be Rio Grande Border Health Clinic. Okay, so that is a great topic to attend. So if any one of you have any questions, please raise your hand or type them in the chat, and we'll try to address them before we leave.